Hello boys and girls, today is the third day of this lecture series, so without any introductions, let's just dive right in. You probably remember the first day when we talk about statistical testing and what is the purpose of the hypothesis. And the test, basically statistical test idea is to test if hypotheses for the population are correct. So there are two types of hypotheses like we talked about. There is the null hypothesis and the alternative hypothesis. The null hypothesis is basically the assumption that there is no difference between two variables. For example, there is no difference how often people from cities or rural area use rubber boots. And alternative hypothesis is the opposite of this, which claims that there is difference between two variables. For example, alternative hypothesis in this case would be there is a difference how often people from cities or rural area use rubber boots. And when choosing statistical test, the choice always depends on the research problem itself, or the level of the measurement variables, or the number of groups which are to be compared. For example, in a case when we have alternative hypothesis, which would be education and gender are associated to each other, the appropriate test would be a chi-square test for cross tabulations. And decision whether or not, or whether this research or not, the null hypothesis is made on the basis of observed significance level of the test, which is called p-value. The p-value is the probability that the result of the sample deviates by an observed amount or even more from the null hypothesis, assuming that the null hypothesis holds true. And the p-value is the probability that the observed deviation from the null hypothesis can be explained by the sampling error alone. Uh, and then you can decide, depending on the p-value, if you reject the null hypothesis. Uh, and also it will indicate the risk of error associated with this decision. Okay, the idea of the p-value is that the lower the p-value is, the more the alternative hypothesis is supported and the more evidence it argues against the null hypothesis. So what is the limit that the p-value must be lower or higher the null hypothesis to be rejected? The most commonly used limit is the 0.05 or 5%. Of course, this is arbitrary limits, so this is what is commonly used, but some psychologists, for example, use the 10% mark. It depends on the researcher. It's a decision to make when you're conducting research. So the idea is that if the p-value is under the 0.05 or 5%, the null hypothesis is rejected and the alternate hypothesis is valid. And if it's higher than a p-value than the 5%, it means that the null hypothesis remains and there is no variation in your results or between the two groups. And here we come to the second part of this p-value argument, the confidence intervals. And they indicate the interval between the actual value of the population variable with a certain probability. And you probably remember when I talked about the how we estimate things. We estimate things in a certain range. For example, we know that the population's height is probably around this area. The estimation is that we don't have the perfect number, we have the mean for that, but there is always the error, which are the confidence intervals, so to speak. For example, in the uppermost picture, there is the t-hat, which indicates the upper interval, and the lower interval is the lower t-hat there. And the mean is somewhere, it's the dot there, but the actual number could be somewhere around that area. And the bottom picture also shows a different form presentation for all the confidence interval. So that's the area where the estimation is, and the mean is on where the line is. As I said, generally we use the 95 confidence level, which is the p-value 0.05, which means we allow 5% of error. It's the inverse of the p-value logic on the previous slide, basically. And it's calculated with the mean, which it's from the mean and plus minus 1.96 times the standard error. As you can see, we can use mean and standard error again. So there's the basic building blocks how you can calculate the confidence interval from the mean. It's that's easy. But when you see these kind of graphs inside of research papers, that's what it means. The confidence interval. That's the elasticity where the number is. That's a bad word to use, but you probably get my point. So even more about statistical testing. Example, if the researcher gets the p-value of 0.001 or 0.1%, the result of the sample is surprising. The p-value of 0.001 must be interpreted as follows. If the null hypothesis is assumed to be correct, then a result similar to the sample or even more deviating from the null hypothesis occurs in one sample out of 1,000. And of course, this is quite like sufficient evidence against the null hypothesis, and the result is no longer surprising if the null hypothesis is not true. It is important to note, of course, that statistical testing never proves the null hypothesis to be correct. It's the other way around. We're trying to like falsify the null hypothesis. And next up is the elaboration. So the idea of elaboration is basically statistical reasoning, of course. And the first of these elaboration things is the additivity. And here we can see we have an independent variable x and a dependent variable y. This is the original association. We think that there is some association between x and y. So the x will affect somehow to the y or has some kind of an association. For example, this is most easier to understand. There is the X is, for example, training. It could be some kind of a job training or education, something that will affect your work performance. And Y is your salary, so how much you can earn. And usually the idea, if you have better training, it will positively increase your salary, of course, in the work. And the C variable here is an additive factor if the association between X and Y does not change or be replicated when the C is introduced to the model, and the association between there is an association between C and Y, and the C and X will also be associated. And the C variable in this case is the work experience. So example, the idea here in the additivity thing is it adds more to the Y, the countervariable C. So example, the work experience of course will have a positive impact on your salary, and the training will also have a positive impact. So it will increase even more the Y variable, which is the salary. So work experience and training add to your salary, but the C in this case as third variable is an additive effect to this. And of course the C and Z will be could be associated together, but this is not the interesting here. The interesting is what it's going to do on the dependent variable Y, which is the salary. So if there is like a one-way street to the Y, this is the additive effect. It adds on the Y. And the second part of the elaboration is spurious correlation. Again, we have the original association here, which is the independent variable x we'll have association between the dependent variable y. This is the original idea of the association logic. But now we are introducing in the model the control variable z, which has the links towards the dependent variable y and the independent variable x. And the central rationalization here is the connection between x and y is apparent if the x and y association disappears when the z variable is introduced in the model. And this is only the disappearance of the association is because z is associated to z and y. And one practical example is this: is if we treat x as or the independent variable as the number of fire trucks and the y as the degree of destruction. Now visualize in your head that there is some kind of fire going on somewhere, and there are coming a number of fire trucks coming on the scene. So there is, of course, not an association between the degree of destruction and the number of fire trucks itself. The fire trucks doesn't uh, cause destruction, so to speak, but we have magnitude of fire, and that magnitude of fire will determine basically the number of fire trucks which are going to come into scene and the degree of destruction. So the control variable, for example, if we would measure just the number of fire trucks and degree of destruction, we would have a false association there. But because of course there is more fire trucks, but the fire trucks doesn't cause the degree of destruction. The thing is here that the magnitude of fire as a variable, if we put that in the model, would basically suppress the association between x and y. That probably makes sense now. Okay, now we go to the third elaboration variation, which is the intervention. Uh, and again, we have the independent variable x and dependent variable y, which is the original association here. And now the z will act as an intervening variable. And this is a little bit the long lost cousin of the spurious correlations, because they have a little bit the same idea behind it, but the idea in this, the nuance is that z occurs over time between x and y. So what does in practical manner mean? The x here is now age, y is a liberator attitude slash sexual explicit like behavior or more openness to sexual acts. Let's just say that well, the culture is more open in that area, and the Z is going to be how religious are you. So the introvert parameter X8, of course, will change your liberal attitudes towards sexuality, because in olden times we were more like uh, conservative than the younger generations. This is replicated in many societies over time. But we have to take account more than that, of course. Over time, what has been changed? It's not just the age, because people will age normally, and the association it isn't like simple as that. For example, Z as a control variable is the how religious people are, and the more religious you are, more conservative you are, especially in sexual behavior. And in the olden times, people were more religious back then, so their behavior were probably molded by this. So if the age will work through itself from this kind of a variable, for example, the old people are more religious, thus they are more behave more conservatively in a sexual manner. So, and the young people who are not that religious probably have more liberal attitude towards sexuality. So there is a channeling effect, so to speak. The Z will work through Z. So it's probably most easier to understand like this. And here we have the last part of the elaboration, which is the interaction. And of course, there is again independent variable x, dependent variable y, the original association. But now the Z is going to be a little bit different than the last time. Okay, the connection between the X and the Y is different in different categories of C. So we have multiple categories what we are watching in a category of C, so to speak. The variable C is split into two parts. And the strengths of the associations may vary in a different groups of C. The association may be lost in one of the groups of C, and the association may go in a different directions in C's groups. And the example here is that the X is a number of children, Y is salary, and Z is gender. So from the variables on, you probably will understand where this is going. So we have a G has two groups. One we have the males, and second we have the females. So the women, of course, are usually or the traditionally, depending on society, uh, stay more often at home with their children all the longer time because they are, of course, the biological sex which goes pregnant and they have to spend more time away from the work. And you can possibly imagine that has an impact on their salary. And of course, usually in traditional household, men is more often who go to the work instead of a woman. So there's disbalance here, which will directly affect their ability to gain salary. And more of the children, of course, more lopsided this impact is going to be. And the idea, of course, here is that the strength of the association may vary in different groups of seeds. So, more children, probably women will spend more time at home, which is time away from the work. So, the Y factor, the salary will go down. And the same thing doesn't happen in the group one, which is the males, of course, if they are spending more time at work. And the association may be lost, or the association may go different direction. Like I said, the men's salaries can go up because they have more opportunities for their career, and the women's can go down or stay stagnant because of this. They are spending more time away from the work. Or there could be totally different results if the society, just say, has a more time off from the work for the men and women. They are split in 50-50 ways. Who knows? But this is the idea of interaction. The y variable go through like a different routes altogether, stay the same, whatever. But this is the one form of elaboration here. And as a summary, we have here all the versions of the elaboration. Just if you want to have a quick reminder what is what. And the arrows are a little bit different in the interaction part, but I think the previous slide is more easier to understand. But that's one traditional way also to put it. And next up is the cross tabulations. And finally, we come to the cross tabulations, or the hands-on part of this thing. And let's just say we have an interest on the connection between residence and a political interest. Here we have a map of this, and the idea behind it is that we would be particularly interested whether the people living in rural areas are less interested in politics. So, of course, this map shows what people do vote, but my point here is that it shows also that how people are having a difference in opinions, and there is lots of variation in different parts of the country, and we have in these clusters of same-minded people, so to speak. So maybe the overall interest also varies in different types of an area. So if we don't have time for in-depth register analysis and causal effects and stuff like this, we could use cross tabulations for just to find this out if there is some kind of an association between it. So this is what cross tabulation is used, finding association not for the heavy duty causal studying. So, of course, the next question is what is the cross tabulation for? Uh, Cross tabulation is usually used to ask whether the distribution of the dependent variable are different in a different categories of independent variable. And the null hypothesis, of course, is there is no correlation between variables x and y, and that's what is being tested. Is there a variation or not? Simple as that. In order to obtain the information whether there is no association between the variables, the percentage, row percentage of the independent variable are calculated. If the different distribution differ between the independent and dependent variables, it can be assumed that there is an association between them. Okay, here is the important part. Uh, like I said previously, that there is types of variables which we can use in different kind of methods. So here in cross tabulation, uh, you need to choose dependent and independent variable on a categorical variable types, and ordinal and nominal variables are totally fine, both of them. And for example, the interest in politics is a dependent variable which is associated with the living environment, which serves as an independent variable. And both of those are categorical variables, of course, because interest in politics is how interested are you, somewhat interested, very interested, living environment, are you in rural area or are you in a large city? Those are categories, not like numerical and data. So here we can see the both of the variables, and the nominal scale variable is the which of the description best describes your living environment, and the ordinal scale one is how interested are you in politics. Ordinal because you can rank these. These are like states of values, and the nominal scale one is just a status of or the description of certain kind of thing. It doesn't inherently have order. So that is basically it's quite straightforward. The main thing here is they're both categorical variables, which we can measure by the shares. So we are back here at again. So our research hypothesis. These are the first things you have to do before you are going to do research. So we are going to go through this again. So our research hypotheses are as follows. First, the null hypothesis. There is no association between people's living environment and a political interest, and our alternative hypothesis is inverse of this. There is association between people's living environment and political interest. And to determine if we can abandon the null hypothesis, we have to use chi-square test to answer to the research question whether the people's living environment and political interest are in factual associated with each other. And the chi-square test is suitable for this purpose as the variables are in nominal and ordinal scale. Okay, here is the example of the table format of cross tabulation. And this is what you see in academic papers, for example. So it's a clean up, nice, and doesn't have any crap from a statistical program or stuff like this. Usually the outputs, what comes out, is something that you cannot publish anywhere. They look like, well, pardon me, but shit. So you have to have clean it up in an Excel or some kind of other program, but Excel is usually used because it's simple, effective, and works every time. So here we have cross tabulation between living environment, which is the independent variable, and the interest in politics, which is the dependent variable. And usually these kind of tables are presented in relative distribution, yes, and per percentage table, basically. And now we see how the variables are put in the table. So we have the independent variable which takes the row position, and the dependent variable takes the columns. And the idea is that if you are doing this every time like this, you are putting the dependent variable on the columns and independent variables on the rows, you get the calculations, and you calculate row per percentage, you get the calculation right every time. But this is for the other statistical programs, etc., because you can usually do a habit where you put the variables in order, right order, for example, in data. But we don't have to worry about that. We can do everything by hand, but this is usually the logic what people are using here. Okay, first thing we should look on is not the center of the table, but the edges of it. So looking at the row per percentages, we have also the difference in relation to totals, or the edge distribution, so to speak, the distribution of the variable to be explained, so to speak. Whether the variables differ can be viewed as differences on the edge distributions. So you can look up the totals and get the big picture quite fast there, at least in the categories of dependent variable. It's pretty easy to do and fast. That's usually what you look up first. And here we have the so-called conditional distributions. And the what is the distribution of dependent variable in each category is the independent variable. And they are called the conditional distribution, here shown with the red circle, for example, which is the one categories of conditional distribution. So if there is no relationship within the tables, the distribution are similar in each class. So there is no variation. All the numbers would be really close to each other, so there is no distribution at all. And the conditional distribution can be more easily compared to the edge distribution and to each other. For example, here, do residents of a large city differ from the people in general, or do the residents of a large city differ from the rural ones? And you can just go through these by uh, shifting your eyes with the colored areas and see per column how they are like differing each others. So we can see that the from the total, big city is much higher the share. They are very interested in politics than overall the country, but the countryside is under the total distribution basically. So they are less interested about politics than the total. Like very interested people in general of these categories of independent variable. So this how you can cross reference how in different dependent variables categories the independent variable categories vary, so to speak. I know that sounds complicated, but when you just look up the numbers, it becomes more obvious. Even if you like just follow the color coded things, and you will understand what I'm saying here. Of course, there is the one question still. After all that, are there any differences between the independent variable and the dependent variable? And in cross tabulations, the test for the statistical association is being tested by a person's chi-square test. And starting assumption is the null hypothesis, of course, which is the values of the variable are independent of each other, or aka there is no relationship between them. And we are going to test that relationship, and if there is a relationship between the variables on the sample and of course in our cross tabulation table. Thus, the observed cell frequencies are compared to the expected values, and I'm going to go through them. How do they work? And now here, the chi-square test is the independence test, which tells how likely it is that the dependence has arisen only as a result of randomness in the sampling, or are the variables independent of each other in the population. And here we have the whole, like the formula or the equation which is calculated, and I have simplified it for you. So we need the expected frequencies and the observed frequencies. So it's basically uh, we sum in all cells all the expected frequencies, which is subtracted with observed frequency, and having exponented with the second, and divided by the expected frequency. And the observed frequencies are quite easy to understand. They are the values in our dataset, and for example, the strains of the political interest. And now we are going to go through the expected frequencies, which are so-called theoretical distribution. Uh, but let's go to the formula and step by step and see if we can make heads or tails of it. Okay, the expected frequencies describe a situation where the conditional distribution of each variable is similar in each category of the other variable. In such situation, there is no statistical association between all the variables. And this corresponds to the null hypothesis of tests. So basically, all the numbers there on the cross tabulation is totally same or really close to same. So there is no variation, which equals null hypothesis. And the test compares the observer table with the table corresponding to the null hypothesis. And so the idea is that we are comparing the theoretical table where there is no variation to the actual data. And if there is a deviation between these two, of course, there is null hypothesis cannot be true then, because there is a difference between those, something that doesn't have difference. So it's quite an ingenious plan. Okay, time for the practicality. So we could use Excel and calculate this all automatically, but let's not be those guys. We like to know what we are talking about. So here let's go this step by step. First, we have to determine what are the expected frequencies. So we need this for the calculation to squeeze chi-square test basically. So we need the observed and the expected frequencies to know if they differ from each other and if the null hypothesis is true. So for the expected frequencies, we need edge distributions for each category and sample of the table. And here is the example. The expected frequencies from the category 1 and the sample A are calculated using the edge distribution of total number of observations. And there is the small formula there. A plus B plus C like multiplied by a plus d plus g and divided by the number of observations here. That's the basic gist of it. Now, second part of the quest for chi-square. Now, let's use the previous slide as an example. Now, expected frequencies are calculated for those who live in large cities and for those who are interested in politics by using the edge distribution there. We have the column there and the row there. With the red circles, we see the number with the yellow yes, it's yellow numbers and the red numbers there. They are multiplied with each other and divided by the total observations, which is on the corner, and that is of course the 1921 individuals here. And then we get the expected frequency of 51.8, which is the uh, those who live in big city and how interested are in politics in that cell, which is the 74 one. And we need to apply this formula and calculate the solution for every cell across the cross tabulation to obtain all the expected frequencies. So you have to do this formula and calculate with every cell inside there per every category, every column, per row combination. So let's go a little bit back and put the whole equation there so you can see now. We have now the expected frequencies, which were calculated with the previous slide's formula, and the observed frequency from the original table. And I have color coded here what is happening inside the equation. So now we are using these yellow ones, which are the determined that there is no, this is the null hypothesis case, there is no variation between the groups, inside the groups, and the observed are the what is the reality in our data. So we are inputting those numbers into that formula, and we are going to get one hell of a equation there. And now, finally, we are here. We can calculate the z-square basically. So there is the formula now where all the numbers are in the example has put in, and we have to repeat also this procedure for every cell. So the formula is going to be really, really long and thick, but then again, that's life. So this one is calculated like in the I have presented, and finally we come to the answer that the value for the chi-square test is 61.6. And now you are probably having a question, and the question is, of course, uh, what what is the 61.6? Good news is, or the bad news, depending on the listener, we are not yet totally done. Now we need to know what is the p-value based on the chi-square test. So we also need something called degrees of freedom, which is the number of variables and their minimum number of cells. And we can calculate this quite simply just using the rows and the columns of our table here. And it's number of rows minus 1 times a number of columns minus 1. So it's pretty easy calculation to do. So if we input these numbers into our formula, we get the degrees of freedom of 12. And we are going to use it in next slide on the table, p-value table. And now finally we are here at the p-value table. And now we have to find the row. There is the degrees of freedom in rows, and the columns we have the appropriate p-value. So first we find the degrees of freedom. Here is 12, and we are going to go through all the way and try to find the appropriate number for the chi-square test. And we don't even come to close because it's 61.6 and we are at the cell which says 32. That's the final cell, which is for the p-value 0.001, which is the one of the highest like p-value or the lowest p-value actually we can get. So we can stop searching from there. So it normally we would go on, but that's the satisfactory point. We get the lowest p-value here, so there is strong statistical uh, uh, correlation between the variables. So the p-value is 0.001. So you have to use this kind of table if you are calculating anything by hand. But of course, statistical programs do this for you, so you don't have to worry about anything. But now you know how do you find the p-value. You have to use this kind of table to obtain it with the information you can calculate from the table itself. So we walk quite a long road, but after that we can go back to a hypothesis. That was what we were asking from the data. So our research hypotheses were the null hypothesis is there is no association between people's living environment and a political interest. And we have the alternative hypothesis that there is association between people's living environment and a political interest. And our chi-square test states that the p-value is lower than 0.001, which invalidates the null hypothesis. Thus, the alternative hypothesis is validated, and we can state there is an association between people's living environment and political interest. So, uh, we did quite a bunch of calculations just to get one number which will validate one thing. Of course, in normal situation, you can uh, do this calculation just in a mere fraction of a second with statistical programs such as Data or SAS or R. depending what you want to use, even with Excel. But these kind of automations usually will hinder your ability also understand how things are obtained or how things work. And again, as we could see, we just needed the just basic numbers what we had on the table, and we could do everything by hand without any fancy magic basically. Just the knowledge about few equations, and that's it. And usually we need just mean or standard deviation. In this case, we had all the information we need at the table itself. And let's take a small bonus round here. The question is what we do with cross tabulation if we should have one more variable here. Uh, let's go way back to the elaboration slide and think about what if would we have set variable along with the political interest and type of area. To keep our example really simple, let's just think that the responded sex as a variable c, and thus we need to split the data in two groups for the cross tabulation. Just think about the interaction elaboration. We could just split the data to two cross tabulations. We have one for men and one for women, and we could compare these results with each other. So everything is neat and simple, and we don't have to play around with a mass amount of tables. So that's the one thing to do when you want to have so-called three-away table and not just single two-away cross tabulation table. Okay, here we go again. So now we have added one more variable here in a form that we have split the data in two tables, but we have put everything in one table here. And this is the cleaned up version here. This is one of the version. There is no standard way to present data, but everything is usually in a scientific journals really minimalistic without any bullshit, so to speak. So here is the cleanup version. The male data is in the left side and the right side has the females. And right away, when we watch the blue circles, which are the interested points here, and we see that there are more males than females who are interested on politics. Because if we watch the columns very interested, it's not, it's just 1.7 times higher about what the males are more interested than the women. So you can see it from there, and the uh, somewhat interested part is 5 percentage units higher, and the not much interested part is much higher on like women. So basically, that tells everything right away, at least in overall. In addition, it seems that the interest in politics is higher in the large cities, and the disinterest in females is much higher there. And you can see this right away also. So the disinterested part in large cities is quite interesting. It's quite high compared to males, but uh, that's how it goes, I guess. Then at least at this table says so. And there were also the difference in interest is quite high because males are 2 times more interested than the women are. So you could do this kind of comparisons between the numbers and um, even more like more calculations and tests, but this is as far as we go today. Okay, don't go away yet. We have few ending remarks here. And what about the I have to say about the cross tabulation is the result of a test can be relied upon if two assumptions are met. Up to 20% of the cells must have frequency below of 5 or something like that, of 5 people there, and the expected frequency shall not be less than 1. So you need certain amount of people to make these calculations work. So in the sales, you cannot have like just one people. It doesn't make any sense. Of course, you don't have any shares or distribution there then. And of course, in the larger sample size, it's easier to chi-square test give statistical significant results, aka small p-values, because um, when you are blowing up the whole like data set much larger, usually the confidence intervals go smaller and smaller because how it's calculated. So usually when you are handling really big data sets, all the p-values are almost every time significant. So you don't watch the p-values, you just watch the effect numbers on the your results. So that's what dictates everything. And I still recommend that you always check just the effect values. It's not that important, the p-value stuff. Of course, you have to have statistical significance in their difference because usually the effect size isn't strong either. But that's the most important part. What the actual effect is? For example, in the previous slide, we have the quite big differences between the males and females in political interest. That is what is interesting, not what the p-value just is. So go through your results, what's the effect size, and just what's the p-value as it. Okay, you can straight away see if there are differences or not. But the effect values are more important there. Okay, here we are at the final slide. And remember kids, correlation doesn't equate causation, and association is not the same as the effect. This need to be hammered in a million times over. I know this is boring probably, and you say, yeah, that's just how it goes, but this is important because people will forget, people will uh, tell these things wrongly in journals, they will do uh, scientific conferences even, they use these words wrongly. These things happen, so it needs to be hammered in every time. For example, here we have a nice graph about number of people who are drowned by falling in the pool and films of that Nicolas Cage has been appeared in. So correlation doesn't mean that there is causation, and of course even anything can be correlated together, even the most absurd things like this. So you have to remember this and think about what you are measuring. Does this make sense? What's my research questions? Why I'm measuring this? What's the point here? And nothing can be said about cause and effect relationship when you're using cross tabulation. Just keep this in mind. And of course, when we think about the association between political interest and residential area, if it would be a causal link, it would mean that if you move in a certain residential area, you just like magically start to uh, be interested about politics. Of course, this is now how it goes. There's just association, and the implications are totally different. So keep that in mind for now, and good luck for these times demos. We have some calculations to be done in Excel again, and hopefully that will go fine and dandy for you. So goodbye for the next time. Peace.